Okay, what we're going to be looking into will be matrices, cofactors, and minors, given matrices. And just starting out with the definition of the determinant of a 2 by 2 matrix. And here we have a 2 by 2 matrix. Okay, where we have a matrix with 2 rows and 2 columns. And the first subscripted value is going to be in reference to the row. Second is going to be in reference to the column. And for the determinant of this particular 2 by 2 matrix, you're looking at taking, upon appearance, okay, diagonal products, where you're taking the difference of them. So you have the upper left times the lower right minus the product of the lower left times the upper right. Okay, so you have a of 1, 1 times a of 2, 2 minus a of 2, 1 times a of 1, 2. And just looking at some examples here, working with 2 by 2 matrices. Say if I have a matrix A with the first row consisting of 2, -3, and the bottom row consisting of 4 and 7. And if I look at the determinant, okay, so looking at the products, so I have 2 times 7, which is going to be 14, and then subtracting the product of 4 and -3. So I'm looking at 14 minus -12, and this will translate to 14 plus 12, which equals 26. And if I take another 2 by 2 matrix, say if I have the top row with 12 and 10, and the bottom row with 4 and -7, and looking at the diagonals, so I have 12 and -7, and the product is going to be -84. The other diagonal, we have 4 times 10, which is 40, and that is going to be deducted. And here we have -84 minus 40 comes out to -124. And looking at square matrices, okay, that have more rows and columns, and just sort of providing a bit of a segue, and we have what are referred to as minors and cofactors. And it says here, to define the determinant of a square matrix of an order higher than 2, it is convenient to use minors and cofactors. And okay, and we have here that if A is a square matrix, then the minor m of ij of the entry I of A of ij is the determinant of the matrix obtained by deleting the ith row and the jth column of A. And the cofactor C of ij of the entry A of ij is going to be where we have the cofactor of I of j is equal to -1 to the I plus j times the minor I of j. And we have, in this particular case, if we have A to be a 3 by 3 matrix, then the minors and the cofactors of A of 2, 1 and A of 2, 2 are shown below. And we have for the minor of 2, 1, where you're looking at involving the second row and the first column, and you're looking at deleting the second row, first column, and you have left exposed. Okay, we have in the determinants. Okay, we have A of 1, 2, A of 1, 3, and then we have A of 3, 2, A of 3, 3. So those are the exposed elements. And for the cofactor, you're looking at -1 to the I plus j, where the I is going to be 2 in reference to the second row, and j we have 1 in reference to the first column. And so you're going to have like -1 to the third, which is a negative, and you have times the minor of what we have with 2, 1. 2 for the row, 1 for the column. And likewise for A of 2, 2. Okay, we have in the pattern, you're looking at deleting the second row as well as the second column, and the minor of 2, 2, we have left exposed. They have A of 1, 1, A of 1, 3, as well as A of 3, 1, and A of 3, 3. And the cofactor, okay, we have -1 to the 2 plus 2, and we have -1 to the fourth, which is going to be a +1, and we have times the minor of 2, 2, and looking at for the sign pattern of cofactors. And this will come into use if I'm looking at working with just the top row, and for the sign pattern for a 3 by 3 matrix, and I look at mainly, or in a lot of the operations, I look at the top rows. They have like a positive and a negative and a positive. So this is what you have for a 3 by 3 matrix. 4 by 4, you have alternating positive and negative signs as you go row by row as well as column by column. And you have continuing on endlessly for n by n matrices. You still maintain the use of alternating positives and negatives. And now, in the case of what we have in the determinant of a 3 by 3 matrix, okay, so we have, let's say we have A is a 3 by 3 matrix where we have the top row consisting of 3, -1, and 7. Middle row we have 5, 0, 2. And the last row we have -2, 3, and -1. And looking at the determinant, now if you notice the plus, minus, and the plus above the 3, the -1, and the 7, this is going to be looking at taking the minors of what we have regarding the top row layer. Okay, notice I have a 3 by 3 matrix, have the top row layer with plus, minus, and plus, and that's going to be applied to the 3, the -1, as well as the 7. Now for the determinant layout, okay, again, I'm just changing the grouping symbols where I have going from brackets to the bars, and this is having nothing to do with absolute value. Now for the determinant of this 3 by 3 matrix, again, you're looking at, like you have positive over 3, and then you have covering up, okay, the top row as well as the first column. Okay, I have left exposed 0, 2, 3, -1, and then I have minus, -1, okay, and covering up, okay, the top row and the middle column, I have exposed 5, 2, -2, and -1, and then I have plus 7, and covering up the top row and the last column, and again I had the exposed elements with 5, 0, -2, and 3. So like the 0, 2, 3, and -1, okay, that would be the minor of 1, 1, and 5, 2, -2, -1, that is going to be the minor of 1, 2. And whereas in the case of 5, 0, -2, 3, that would be the minor of 1, 3 in reference to the first row and the last column. And we're going to get back to this. And we have with the 2 by 2 determinants, okay, so you're going to have 3. And again, taking the diagonal products, okay, this is going to come out to -6. We have 3 times -6 is -18. And we have minus -1, so that would be a plus 1. And taking the diagonal products, okay, so you got -5 minus -4, and this is going to be -5 plus 4, which is -1. And so we have 1 times -1 is -1. And then we have 7, and we have with the 2 by 2 determinant, okay, which in this case is going to be 15 minus 0, which will lock in at 15. So we have 7 times 15 is 105. And clustering together, okay, so you got -18 minus 1 is -19. In turn, we have -19 plus 105 comes out to 86. And let's say that if I have another 3 by 3 matrix, okay, so I have the top row different this time. The middle and bottom rows will stay the same. So the top row have changing over to 12, 10, and 0. And we have for the value of the determinant, okay, so looking at 12 times what's going to be the minor of the first row in the first column. So you still have again 0, 2, 3, -1, and I have minus 10 times the minor of the first row and the second column. So you still have exposed 5, 2, -2, -1, and I have plus 0 times the minor of the first row and the last column where you have 5, 0, -2, and 3 exposed. And so you still have the same values, still working with the same minors, but you have different coefficients, okay, from what we have with the top row elements. Okay, so you have 12 times -6 minus 10 times -1, and since we had 0 at the tail end, we just left that out. And so looking at combining, so I have -72 plus 10, which comes out to -62. Now, in the case of a 4 by 4 matrix, okay, notice you have, for this, okay, you have alternating positive, negative, and again, that would be in reference to the positive 12 minus 10 plus 0 minus -1. And looking at the value of the determinant, okay, so looking at 12 times, what would be the minor of the first row, first column? And I have minus 10 times the minor of what would be the first row, second column, and I have 0 times what is going to be the minor of the first row, third column, and I have minus -1 times what would be the minor of the first row, and last column. And so just looking at what we have here, okay, so you got 12 and the minor of the first row, first column, ultimately that is going to translate to 22. And we have, in the case of minus 10, okay, we have minus 10 times the minor of the first row, second column, so that would be negative 13. And then we have, again, so 0, that is negligible, so just moving forward, okay, to what's going to be plus 1 times the minor, again, of the first row, last column, and just following through with the determinants. Okay, so just carrying out these operations over the determinants in the intermediate steps like what I had with these items earlier. Okay, we have the last minor. Okay, that turns out to be 25. 12 times 22 is 264. And we have negative 10 times negative 13 is 130. And we have plus 25. So the value of the determinant of this particular 4x4 matrix comes out to 419. Okay, so in looking at the determination of cofactors and minors, and going back to our first matrix, which we had to be a 2x2, and we have the matrix A, again, which we looked in the first example, consisting of the top row with 2, negative 3, bottom row with 4 and 7. And again, for the value of the cofactor of the ith row in the jth column, you're looking at the exponential base negative 1 to the I plus j power, and you have times the minor of the ith row, jth column. And let's say that in reference to the first row and first column for the cofactor. Okay, you have the row and the column, okay, to be the first. Okay, so covering up the first row and the first column, we have exposed the value of 7. And negative 1 to the 1 plus 1 is negative 1 squared, which is positive 1. And you have times the determinant of 7. And for this 1x1 section, that is only 7. And we're not looking at absolute value. And we have 1 times 7 comes out to 7. Now for the first row, second column. So if I cover up the first row and the second column, I have 4 left exposed. And for the degree to which negative 1 is raised, I have to the 1 plus 2 degree, and negative 1 to the third is a negative 1. And we have times 4. Negative 1 times 4 comes out to negative 4. And for what we have for the determination, the cofactor of the second row, first column, so if I cover up the second row, first column values, only negative 3 is going to be left. And again, we're just looking at the determinant of just negative 3, which is minus 3. Again, in spite of what the symbolism might be, we're not looking at absolute value in this context. And again, for the sum of the I and the j positions, again, we have 2 plus 1 is 3, negative 1 cubed is negative 1, and again, negative 1 times the minor value of negative 3 comes out to positive 3. And for the second row, second column, again, we have negative 1 is going to be to the 2 plus 2, in this case, negative 1 to the fourth. And we have for the minor of the second row, second column, so if I cover up second row, first column, or made that second column, I have left exposed the value of 2. Negative 1 to the fourth is 1, and you have times 2, and so this will come out to 2 itself. Now for the cofactors of what we have for the second 2x2 matrix, or the second matrix we found out the determinant of. Again, we have 12, 10 at the top, 4, negative 7 on the bottom. And for the cofactor of the first row, first column, again, I have left exposed negative 7, and the degree to which negative 1 is raised, again, you have to the 1 plus 1 degree, or in this case of the second, negative 1 squared is 1, and you have times negative 7, so this is minus 7. And for the cofactor of the first row, second column, so covering up the first row and the second column, I have 4 left exposed. And again, the sum of the row and column positions comes out to 3. Negative 1 to the third is negative 1. And then I have times 4, which is negative 4. And for the second row, first column, for the cofactor value, and setting things up, now I got negative 1 to the 2 plus 1, which is negative 1 cubed, or minus 1. And for the minor of the second row, first column, again, covering up the second row and the first column elements, I have 10 exposed. And negative 1 times 10 comes out to minus 10. And for the remaining cofactor determination, where we have regarding the second row, second column, and again we have negative 1 to the 2 plus 2 is negative 1 to the fourth, which is positive 1. And for the minor of the second row, second column, I have 12 left over, and we have 1 times 12 comes out to 12. And again, for the monstrous 4x4 matrix, if I'm looking at the just the top row, okay, so if I'm looking at like the cofactor of the first row, first column, and we have, in this particular case, for the first row, first column, I have like negative 1 to the 1 plus 1, which is negative 1 squared, which is 1. And again, for the minor of the first row, first column, again, I have 0 to 4, 3, negative 1, 0, 1, 2, 1 exposed. And we had determined this earlier, whenever we had determined the overall determinant of this 4x4 matrix, and the determinant of what I have here with this 3x3 section is 22, and we have 1 times 22 is 22. And we had also worked with the first row and the second column positions, where we have like minus 10 times the exposed elements. And again, for the minor, okay, you have covering up the top row and the second column values. Again, we have for the minor of 1, 2, again, you have exposed, you have 5, 2, 4, negative 2, negative 1, 0, as well as 1, 2, and 1. And we had found that particular determinant portion to be negative 13. And for the base, negative 1, again, that is to the 1 plus 2 degree, and negative 1 to the third comes out to minus 1. So for the cofactor of the first row, second column comes out to positive 13. And for what we have in the case of the cofactor of the first row, third column, and we bypassed that when we were looking at the determinant of this particular 4x4 matrix, because the top value was 0, and we just rendered that whole thing as negligible. But for the first row, third column, again, we have negative 1 to the I plus j is going to be negative 1 to the 1 plus 3, which is going to be negative 1 to the fourth. And again, for the minor of the first row, third column, again, you have what would be left exposed with 5, 0, 4, negative 2, 3, 0, 1, 1, and 1. And if I were to have taken the determinant of this 3x3 section, this would come out to negative 5. And for negative 1 to the fourth, again, we have at 1, multiplying by negative 5, and we had the outcome at minus 5. And we have for the remainder of what is in the top row and with the last column. Okay, so we have covering up the top row and the last column elements. So I have 5, 0, 2, negative 2, 3, negative 1, 1, 1, 2, which would form the minor of the first row, fourth column. And again, for negative 1, you had to the 1 plus 4 power, which is negative 1 to the fifth. And we have negative 1. And again, for the minor of the first row and the last column. And again, just going back to what we had earlier, I guess you can say sort of like eons ago, you have like 1 times 25 from earlier. Again, the value of that minor is at 25, and negative 1 times 25 comes out to negative 25.